Welcome to lecture 19. In the last class, we discussed about the measurement of compressibility of soft soils in particular. This is a very important topic for soft soils, particularly fine-grained ones, which means usually we talk of silts and clays. Generally, sands are not very compressible. It's not very serious problem in case of coarse-grained soil. We try to study the compressibility in what is called as a consolidation test, or you may say odometer test. So the test is called, the ring is called odometer, and we said we'll put the sample here. Usually we take it from the ground by some sampling technique, provide a filter paper, put a porous stone on top and bottom, and then you apply the load through the center, put a dial gauge here so that you can measure the displacement. And we increase the load increment. We start with something like 6.25 kPa and we go in multiples of 2. We call it as increments which are equal to the current load. So next would be 12.5, 25, 50, 100, 200, 400, 800, etc. kPa. Usually we go maximum up to 1600 kPa. And then we start unloading from 1600, we come to 400, then we come to 100, 25 and 6.25. Each load is kept for roughly 24 hours. The readings of the dial gauge are taken at different time intervals. So time, dial gauge reading, and compression or delta, you can say. So we start with 0.25 minutes, 1, 2.25, 4, 6.25, 9, 16, and then you can go on up to 24 hours. 16, let's say 20.25, 25, 36, 49, 81, 100, and like this you go up to 1440 minutes. T is in minutes. And we'll get readings here. Let us say here it is some 11.00. This becomes say 10.44. And then the difference will give me the compression, which is 0.56, which is usually in millimeters. So we'll end up getting compression under various different times, and then we can take the final compression here. So you know how much is the total settlement under a given load. If I know the compression, I can also calculate the change in void ratio. If you remember, we said that this odometer is called, test is called one-dimensional compression. The sample can deform only in the vertical direction, so the displacement delta is vertical. The sides are inside a rigid ring, so I would say the horizontal strain is 0. So when I look at it, epsilon in the z direction is say delta by h. Delta is the compression, h is the initial thickness, or let's say we call it h naught. It is also equal to change in volume by initial volume, or V naught. And this I can show is the same as delta E by 1 plus E naught, because if you look at the sample here, the solid grains are incompressible. So any change in volume is due to change in void ratio. So if there is a certain compression, corresponding to that you will have a corresponding change in void ratio, because the grains do not compress at all. So what we then do is convert the strain, and I get the change in void ratio for each increment. So let us say under the Q, 6.25, 12.5, 25, 50, 100, 200, 400, etc. you will have delta. I'm starting with 0, let's say some 0.15 millimeters to 7.43, 0.56, something like this. You can calculate strain is equal to delta by H naught is equal to delta E by 1 plus C naught, which means the change in void ratio is equal to delta into 1 plus C naught by H naught. What is H naught? Is the initial thickness of the sample, and E naught is the initial void ratio. And how do we get it? We know that E or E naught is equal to G into W naught, where W naught is the initial water content, and we are assuming the soil to be saturated for S is equal to 1 or 100%. That is 100% degree of saturation. We also said that G is the specific gravity of the soil solids. If I know the water content, which is very easy to find out, all that you do is you take a sample, put it in the oven, find out the loss due to heating divided by the dry weight of the soil, we get the water content. If you know the water content, you can get the void ratio. And once you have the void ratio, initial void ratio, you know the change in void ratio under each increment, so that I can find out here E naught, then E for 12.5, E for 25, like that I can get E for 800 kPa, etc. So you will have void ratio corresponding to the stress, which is of course in kilopascal. So once you have, you can plot the variation of void ratio with effective stress, that is the applied stress and the final reading you are talking of. Can I plot here E versus what I call sigma prime, or you can say Q, which I want to put it? You will find that the curves come something like this. If I unload now, I find that the curve comes and bounce back here. So I can say this is the loading curve, this is the unloading curve. When you remove the load, the soil bounces back. Soil is not elastic, so you will not get full recovery, but you will get only partial recovery. Now if you have a curve, you can see that E decreases as you increase the effective stress or the load on the sample, but the change is smaller and smaller. Suppose I look here, for a small increment, the void ratio change is delta E1. For the same increment next, you will see that this difference E2 is less than delta E1. Similarly, if I now look at somewhere here, delta EI is less than delta EI minus 1. Each succeeding increment gives you a smaller change in void ratio, smaller settlement. Do you know why? Because if the soil has compressed, it has become more dense. Because if void ratio is less, soil is denser. A denser soil has less compressibility. And so what you find is this curve is concave upward, which means the shape is with decreasing slope, and which means it's becoming less compressible. You can say here, whereas here towards the end it is less compressible. We have defined a parameter called A sub V, called coefficient of compressibility, which is equal to change in void ratio by change in effective stress, which means I am now looking at this is delta sigma and this is delta EI. So I can take the ratio of the change in void ratio with respect to change in effective stress, and that is called coefficient of compressibility, and we define it by the symbol A sub V. And you know that AB decreases with sigma prime. As you increase the stress, the ratio or the compressibility decreases. Now this is not a very convenient term, so what we have found is if I can divide this AV with the initial volume, which is corresponding to 1 plus C, we get coefficient of volume change. We use the symbol m sub v. M sub v is equal to a sub v by 1 plus C naught. What does it mean? This is with respect to, for a unit solid volume, this is the void volume, and so 1 plus C naught gives me the total volume. And now we can show this is delta E by 1 plus E naught by delta sigma. AV is nothing but delta E by delta sigma. Now you can see that this is nothing but epsilon change in volumetric strain by delta sigma prime, or I can say vertical strain by delta sigma prime. You agree that the axial strain is equal to the volumetric strain because the area remains constant. If the area remains constant, vertical strain is equal to the volumetric strain. And you find that here you have strain by stress, which is a very inconvenient way, but historically in geotechnical engineering, Tazagi came out with this parameter and we continue to do it, except in the last 30-40 years we found another term, D is called the constraint modulus, is equal to delta sigma prime by delta epsilon z, or delta sigma prime by delta volumetric strain, which means it becomes 1 by mv. And now we have a standard measure like modulus of velocity, Young's modulus, where you have stress by strain. You can see later D is a function of E, which is the modulus of deformation when you do a test by axial compression. Say you put delta sigma and then you find the strain, and here of course the sample is not confined, whereas in our case the sample is confined. Because the sample is confined, you call it as constraint modulus. So if you again plot, for example, AV is decreasing with stress, with increasing stress. So MV also will decrease because this denominator is nothing but a constant. 1 plus C naught is the initial unit volume. So MV also decreases. Or if I plot constraint modulus D, if I am plotting D is equal to 1 by mv, and again sigma, it turns out to be, it increases, which is as it should be, because with increasing stress soil is becoming denser and stiffer. So you can say soil becomes denser and stiffer with increasing stress, which means suppose I am constructing a tall building, I construct the first floor, which will give an increase of load of 10 kPa. It will undergo certain settlement. If you now go for the second floor, for the same increment in stress, the settlement will be lesser than what it is under the first increment. Suppose you go to the third story and increase again by 10 kPa, the settlement due to the third floor will be less than that due to second floor, or which again is less than that due to first floor. With increasing stress, you will have less and less settlements, which means this parameter, both m sub v, AV, m sub v and D, they are all functions of stress. The first two decrease, the third one, constraint modulus, increases with sigma prime. So it's a kind of, we know it happens, but not a very convenient way of defining a parameter, because you don't want a stress dependent parameter. Suppose you say I want to estimate the settlement due to some structure. It could be a liquid storage tank. Does it mean when you increase the height of the fluid inside from 2 to 3 meters, 3 to 4 meters, 4 to 5 meters, each time you have to take a different value of A sub v, m sub v or D? Is there a better way of defining this variation? And they found in fact there is something unique about it. If only you plot the effective stress on log scale. That means the same plot, we use with x-axis on a log scale. So I'm still plotting void ratio, but I'm plotting log sigma prime. So this becomes 1, 10, 100 and 1000 kPa. Please remember, you can easily design, or for that matter if you go to Excel sheet, you buy a graph paper, you get the plots wherein either one of the axes is on a log scale or both the axes are on log scale. If you do that, you'll find a very interesting behavior. If I take a sample from the ground, let's say I had taken, here is the ground level, groundwater level is somewhere here. I taken a sample from a depth z, say z is equal to 5 meters. I taken it from 5 meters from the ground, and then I put it in the odometer or the consolidation sample. And once I remove it, you have removed or unloaded the stress. Whatever stress that is acting here is unloaded, and you start again. And that is why you get a flat curve, and then you find a straight line in the major portion of it. And then if you unload, this is loading and this part is unloading. And you can see that this part is almost a straight line. So we define the slope as Cc. If you get a straight line, it means the slope is constant, and that's a much better parameter because you have a constant parameter there. So what we now say is that define compression index C sub C is equal to change in void ratio and say delta log sigma. So I can say delta by, or can I say the increment is from sigma 1 to sigma 2. You have increased the stress on the sample from say 50 to 100 kPa or 100 to 200 kPa or whatever it is. Then I'm looking at the change. Delta log sigma means log sigma 2 minus log sigma 1. You can also write it as delta E by log sigma 2 by sigma 1. Put the, first we show that it's effective stress. And this Cc is constant over a large stress range. That makes it easy for us to define that Cc can be 0.3, 0.4, 0.7, whatever it is, and say that over a large stress range, compression index is constant. Similarly, if I look at the unloading part, which we said is here, I can say it's almost like a straight line. We define it as Cs. It is swell index or swelling index, which is equal to delta E by, now I'll have to say sigma 1 minus sigma 2. If I unload it from this value to this value, I take the ratio. In order to make it positive, I always have to use a higher value in the numerator and a smaller value in the denominator. This gives me the slope of the unloading curve. It's very interesting that Cs by Cc is usually of the order of 5 to 15%. So if you have a compression index of something like 0.4, the swelling index could be of the order of only 1/10 of that, which means 0.04. What does it mean? If it is settles by 10 millimeters, when you unload, it will only rebound by 1 or 1.5 millimeters. Soils try to compress, but when you remove the load, the particles cannot bounce back. They are not like steel, copper, and to a large extent even concrete, all other civil engineering materials, which are, you can say, more or less elastic. But soils are not elastic, and they are highly inelastic, so the permanent or plastic deformation is very, very high. And because of that, Cs by Cc is very small, not 0.2 if you want to write it as a decimal. Occasionally you may get up to about 0.2, but you will not ever get something like 100% or even 50% recovery. So what you have now found out is, by plotting void ratio with log of effective stress, you get a straight line. There's also a very interesting thing you might have noticed, that initially the curve is flat, then it becomes steeper. And when I unload, the curve is again flat. So what does it mean? So let us say we'll do the same thing in the lab and load, unload and reload. I'll take the sample. I plot initially, it come up to here. If I unload, this is loading, and to make it a little more obvious, make the drop a bit steeper, and if I reload, it comes something like this. This is unload and this is reload. Can you see there is some similarity? These two curves look similar. What you have done is started with something like, let's say 6.25 kPa. You have gone up to, let's say 100 kPa. Again come back to maybe something like 25 kPa and reload it. There's a slight loop here, but what you find is this reload part of the curve, A, B, C, D, and let's say E. A to B is flat, B to C is very steep, C to D is again flat, and DEC is again flat. And DEC, the curve, is similar to AB. This part of the curve is similar to this. It probably tells you that maybe from A to B it is reloading and not first time loading. And how do you justify that? You agree that when the sample is in the ground, there was already some effective stress acting on that. When you took the sample out of the ground, that effective stress is unloaded. You have put the sample in the odometer or consolidometer and you started loading it. So to that extent it is reloading because the sample already had experienced some stress which got relieved because of sampling and bringing it to the laboratory, putting in the odometer. After that you have reloaded. So this reloading and this reloading seem to be very, very similar, and that could be the reason why the curves are similar. So this reloading is same as this reloading from field. Sample in the field had some stress which got relieved and it got reloaded. That gives an idea. Is there a way in which I can find out what was the maximum stress the sample has experienced in the past? I don't know, maybe if I take a sample from 7 meters, 10 meters, the stresses will be different. This is 5 meters, say this is 7.5, and this sample is at 10 meters. So you agree that the initial stress varies for each of these samples. Is there a way in which we can find out from the log plot or this E-log-P plot whether I can find out what was the stress acting in the field at this location? Casa Grande gave one simple construction in order to find that out. So what he said was, or the method he gave, it is called, Casa Grande was a professor at Harvard in the 1930s and 40s up to about 1960s. It's called Casa Grande's method to determine the maximum past pressure the soil sample has experienced. You can figure out if this sample had experienced some stress and what is that stress. So what he said was, or the method he gave, he said you plot the E-log sigma plot and say the curve is something like this. What we do is, this is the experimental plot. This curve A, B, C, D is obtained from consolidation. He said pick up the point of maximum curvature, which means the shortest radius. So if I look at it here, I can get somewhere here. You can see this is flatter, this is also flat. A straight line has a radius of curvature of infinity, which means it's a huge curvature is very, very low. Whereas a circle will have the smallest one. So at this point we draw a tangent to the curve. Say PD, BD is tangent to load to the E-log sigma prime curve point of maximum curvature, which means minimum radius. If I fit in a curve or a circle, the radius will be very small. At that point, through that you draw a horizontal line. So BE is a horizontal line. Now you can draw angular bisector, so that this angle is equal to this angle. So what is BF? BF is angular bisector, which means EBF is equal to angle FBD. This angle, the angle between BE and BD, is divided equally by simple geometric construction. Now we are supposed to extend this straight line where it will intersect the angular bisector at a point G. You extend the straight line portion back and then see where it intersects the angular bisector. So G is the point of intersection between extended linear E log sigma curve and the angular bisector. What did we do? We extended this straight line and we found out intersection with this line, and that point is called the point of maximum pass pressure. I simply drop a line and I get what is called as sigma dash C, or many times in the books they call it PC. It is called the maximum past consolidation stress. Sigma dash C or PC are called the maximum past consolidation stress. It tells you what the soil has experienced in its past. That is one of the best measures of finding out what experience the soil sample had undergone corresponding to the depth we took it from. So this is a very simple construction. What you did is an odometer test, plotted from the results there void ratio versus log of effective stress. You find that initially the curve is flat, later also it is flat or straight line, so not flat, linear, but in between it changes shape very sharply. You pick up the point of maximum curvature, which means the smallest radius. At that point, draw a tangent. You also draw a horizontal line and divide the two to get the angular bisector. Extend the linear portion back, and where you find the intersection, that corresponds to the maximum pass consolidation pressure. So you have determined now sigma dash C, you have arc called P dash C or PC, which is the maximum consolidation stress. We also know what is the initial stress or the existing stress is the current effective stress of the sample. How do you find out? The other day we discussed how to get so let us say this is the ground level. You have taken, and here is the groundwater level. This is say 5 meters. The saturated unit weight is say 18.5 kilonewton per meter. So the total stress sigma Z at Z is equal to 5 meters is 5 into 18.5. That will give me 92.5 kPa. Let's say the groundwater level is at 1 meter. So this means this head is 4 meters. Pore pressure is equal to 9.8 into 4, which gives me something like 39.6 kPa. And now you find out the current effective stress. Sigma Z prime is equal to sigma Z minus U, which is equal to 92.5 minus, say, let's say 40, just become 52.5 kPa. So the soil currently is under a stress of 52.5. By your construction, you have found out the stress to be sigma dash C or PC. Now they can be same or they can be different. How does it happen that they can be different? To show that, we now define another parameter called OCR, over consolidation ratio, which is equal to PC by P naught. Maximum pass pressure divided by the current effective stress. This is called the over consolidation ratio. We always use the abbreviation OCR. Now this OCR generally can be 1 or more, occasionally can be less than 1. If OCR is equal to 1, we call the soil as normally consolidated. The soil is under the same stress in the past and even now. If OCR is more than 1, we call it as over consolidated soil. What happened? How come the past pressure is more than the current one? Let us say in the geologic history, the ground level, original ground level is somewhere here. By some tectonic activity, current or present ground level is here. What happened? This amount of soil has been removed. So there has been unloading in the past. We don't know what happened. Maybe the river came and eroded. For example, there was a river flowing like this and erosion took it away. Or look at the other way. That soil which has been below has been lifted, like in the Himalayas. There are different ways in which soil will generate a maximum past pressure more than the current one. Most often, of course, is the erosion that leads, if I am removing this amount of soil, it was subjected to ground level here. I am looking at the sample here. It was under a height Z0, but now when we went in to do the analysis, say there was a mountain there. You wanted to level that, so there is ground here, and you want to make a flat surface. So what did you do? You removed this material, put it here. If I now look at a sample here, it was under higher stress, but now because you removed the soil, it is under less stress. Soil becomes over consolidated. There are few situations in the world where OCR is less than 1. One of them is off the Ganges into Bay of Bengal. Ganges is bringing lot of sediment and depositing, and the sea is not yet consolidating, and so the current effective stress is less than the maximum past pressure is less than the current stress because the pore pressures, and because of that it will. And we define this now. Suppose if I have OCR is something like 1 to 3 or 2.5, we call it lightly over consolidated. 2.5 to 10 is say over consolidated. More than 10 is heavily over consolidated. You find this heavily over consolidated soils in the Himalayas. In most of our coastal areas, we get only over consolidation ratio of something like 1 to 3, 4, etc. So what you found now is that the soils can exist in a state where the current stress is less than the maximum past stress. And soil has an ability to remember, and it shows by this construction. And that is one of the very unique features of soil, that it can remember the maximum past pressure. No other engineering material has this kind of memory. So we see that now we found out how to characterize the slope by CC and CS. We can determine the maximum past pressure, and we can define a term called OCR, which will tell us the state in which the soil is existing.